the problem number 2, you have two blocks and they are connected by a string. And if you do a little sketch of it, so we have a block 1, and we have a block 2. So mass of block 1, 16 kilograms. Mass of block 2 is 24 kilograms. And then they are connected by a string, so you come here with a string. And there is a horizontal force of 120 newtons that is exerted on block M2. So this is this force of 120 newtons is clearly acting on block number 2. So we have a force of 120 newtons to the right, which is pulling the system. So we have two things to the term. One is acceleration, and the other one is the tension of the cord. So we have a tension right here, right? So to find acceleration, when you have concatenated problems like those, like this one, you have two blocks connecting by a string. There are ways of doing. The simplest one is when you imagine these two blocks to be just one, right? One block and another one, and the altogether mass of these two blocks is 40 kilograms. So we have a block of 40 kilograms that is being pulled by 120 newtons force to the right, and in this case it's a frictionless, so we don't have friction on it. We have also the weight, we have the normal force, but since they don't act in the direction of motion, we don't need to worry about them now. So if this is the only case and you apply the Newton's law on this situation, so sum of forces along the x direction is equal ma, then the only force is 120 newtons, since friction is not an issue, is equal 40 kilograms it's 40 times acceleration. Then we can derive the acceleration as being 3 meters per second in a positive x direction. So we can get that. But in this case, since we want to find the tension connecting these two blocks, perhaps the best way to deal with this problem is to separate the blocks, and then you do your free body diagram on each block. So for the first block, we have a tension force that is pulling to the right. So this tension, several of you call 120, but this is not the case. 120 is applied to block number 2, not to the block number 1. Okay? So again, since you don't have friction resisting the motion, and you apply Newton's law on this case, tension is equal 16 times acceleration. So we don't know tension, we don't know acceleration, we can't do much here. So we are pretty much stuck. And some of you attempted this approach. Now, when you go to the second block to move and determine the second possible equation we can apply, and we do our free body diagram on it, and I'm not connecting the vectors all the way to the box because for some reason I highlight and I get some funny thing. See, I don't want to do that. And I'm still learning how to use this tablet here. But anyways, so you have a force to the right, and the tension, this tension here now, is pulling the block to the left, is retarding the motion. So the tension is not the same forces as pulls block number 1, but is the action-reaction force of it. Okay, so which means this T force or tension has the same magnitude as this one, but it acts on an opposite direction. Okay, so when you do Newton's second law of motion on this situation, here's what you got: 120 newtons minus tension is equal mass of that block, which is 24, times acceleration. And with this we get our second equation. So we have one equation here, and you have another equation over there. Well, one thing we can do is to take this tension value and then plug it directly in here, and that's what I will do now. So 120 minus 16A is equal 24A, and then we can derive, if we add 16A to both sides of the equation, we ended up finding our acceleration to be 3 meters per square second. And once we have acceleration, right, we plug it, oops, sorry, see, I don't understand why this thing happened. We take this acceleration and put it in here to find a tension that is 48 Newton. Okay. The problem number 3 is one that implies in the knowledge of potential energy. Potential energy of a spring that has been compressed is equal to half the spring constant times how much of this spring has been compressed or stretched. So again, del X is not the size or the length of the spring, but is how much of it is being either compressed from its relaxed configuration or stretched from its relaxed configuration. The spring constant is given. The spring constant is given, is right here, K, right? So the block has a mass of 3 kilograms, so let's use our given information, 3 kilograms, that's the mass of block. The spring constant K is also given, 875 Newton per meter, and the much of the spring that has been compressed is 0.07 meters. So what is the spring potential energy? This is just a way of, hey, can you plug numbers in an equation? Is equal half times 875 times 0.07 square. And then you have a number. I don't have a calculator right in front of me right now, but you have that in joules. So this is energy that has been stored in the spring. So basically the idea is you have a relaxed spring like this. Oh geez, I don't know why this happened. We have a relaxed spring like that, and then what you do, you compress it because you bring a block and you force the block to stay at that configuration. So your spring in fact has been compressed. Oops. Your spring has been compressed of this much here. This is your del X, right? Okay. And del X is 0.07. Okay. So you compress that. So this spring has energy. It can do work. It can do things. It can move the block to the right. So that comes to the second part, part B. If the block is now released and the surface is frictionless, so we don't have friction in here, calculate the block speed right after leaving. So which means go back to here, and now your spring is back into relaxation mode, and the block is pretty much leaving now. So the block is free from the spring. The spring is not connected to the block anymore. The block has a speed, in fact has a velocity or has a speed. Why is that? Because that entire potential energy that we saw in here, we calculate in here, that potential energy is now transformed into a different type of energy called kinetic energy. Kinetic energy is half mv squared. And I had a couple of students who they thought that this K over here is kinetic energy. So you have to know, what apples are and what bananas are and what lemons are. I mean, they are different things, right? So kinetic energy is given by half mv squared. So if you want to know what is the block speed, it's right here. So we make it our potential energy previously calculated equal to the kinetic energy. The mass is given v squared, and then we can determine speed. The speed is equal to times the potential energy divided by 3, square root of that. Okay, that is the problem number 3. Let's take a look at this one. So we have a ski that leaves a ski jump. That's a ski jump right here, and the angle. Oh, I don't like when this happened. So there is an angle here. See if I can write without making this messy thing. Okay, I was able to. So there is an angle theta, which we don't know. We need to find that. And so let's make the person, the skier, as a ball. So so it's right here. So leaves this place, and here's what happened. It comes in a curve. Man, I hate that. It goes like this. And then falls with a parabola. It's not a good parabola what I did. But what is interesting is this curve. Let me see if I can do up here. This curve, that's the ski jumper. When the guy leaves, that's the continuation of that. When the guy leaves, let's say it leaves at this point. When it leaves, it starts curving. Oh boy, there you go. This is a bad sketch. But what I'm trying to say is, when it leaves, the curve is tangent to the continuation of the ski jump, right? So it's not. Some of you did the following. Here's the ski jump. This is the skier going like this, reaching maximum height, and then you have a triangle, right? So you want to find the maximum height is given 4.5. So we want to find this angle, and then you have a 15 meters per second releasing velocity, which is initial velocity, and then you operate the entire problem based on these premises of this triangle, which is not correct. So 4.5 is this maximum height right here, right there, right? But it's not the same as just pulling a continuation, a straight line in there. So you cannot make a right triangle with 4.5 as the height. So what do you need to do? So we want to find, well, what do you need to find in here? What are the given information? We have the initial velocity in which the skier leaves is 15 meters per second. The angle is an unknown. In fact, we have to find this angle. And we want to find the speed at this point. What is the speed at the maximum height? We don't know. So you can use your knowledge of projectile motion we learned in chapter 3 to figure that out. But you can also use conservation of energy. It's much simpler. So you take point A as the point where the skier jumps, and point B, the maximum height, right there. And then what you do, we do a little table with your energy considerations, A and B, and then you go down the list of possible energies. Remember, we did so many times in class. What do we have kinetic energy in A and B? Well, let's take a look at A. In A, I do have kinetic energy because the person is jumping with a speed, half m mass of that person times its velocity squared. So I have that. And in B, I do have velocity, right? I do the same thing, except I don't know the velocity, I put v. So I'm done with my kinetic energy. Do I have a spring in there? Because the spring, as we saw in the previous problem, has a potential energy equal to half the spring force, or spring constant, del x squared or del y squared, depending on which direction the spring is being compressed or stretched. No, I don't have a spring in this problem, so I don't need to worry about it. But I do have gravitational potential energy. I do have that. So let's find out what do I got. Well, gravitational potential energy is equal to, in point A, if I take, by the way, 4.5 above the level, so in fact it is 1.54, is more like this, huh? Right? Oh boy, I really don't like this thing. It's terrible. It's something that I have to learn how to avoid these problems. So that's 4.5 meters is with respect to this up level here. Okay, let me erase this much, and right. So this is 4.5. 4.5 meters is right here. This is the height. Okay, so in respect to the ground level of where the ski jumper jumps, the gravitational potential energy at that point is zero joules. At the maximum height is going to be m, mass of that person with the ski, times g times the height, which is 4.5, right? mgh, the vertical displacement. So then what I do next is, do I have any other energy? Do I have air resistance considered here? No. Do I have friction? No. So that's it. So total energy at point A has to be equal to total energy at point B. So then what I do next is half m 15 squared is equal half m v squared plus n times 9.8 times 4.5 times and times. Well, and then you say, well, I have one equation and two unknowns. I don't know v and I don't know m. I'm pretty much screwed. Well, but you can simplify m, right? You can cancel that out, and then you have a single equation in v. You can solve for v. Okay. So when you go to the part B, is how can you find theta? Well, so v, the velocity, so let me write the velocity at highest point is the one in which the projection of velocity in the y direction is zero, right? Remember your projectile motion? When you reach the highest projectile motion, you divide it in two major components, x and y. The y component has an acceleration in it, and that is g. That is 9.8. It's always pointing downward. And in the x component has no acceleration as long as you are ignoring air resistance. So it's the motion in which its velocity is always constant. So Vx, which is equal to V naught, the initial velocity cosine theta, is always constant. Now the interesting aspect of it is you realize that your Vx, in fact your velocity, the value of velocity at highest point, let me repeat this, is also, the magnitude of it is equal to Vx, right? Because velocity at any part of the curve can be projected in Vx and Vy, right? So in the beginning, that's what you got. At exactly at point A, I have my initial velocity here, and I have my Vx, which is V naught cosine theta, and I have my Vy, which is V naught sine theta, whatever that theta is. And these two components changed because the velocity keeps changing all the way. So if you have a, let me use this part here. If you go to this part of the curve, your velocity component tangent to the curve, it's not real tangent, is given like this, so you bring it here, right? So you do have your Vx the same. Vx is always the same, equal to V naught cosine of that initial theta, and the Vy projection is changing now. The Vy is the only changing. So your velocity at any given point of that curve is always given by a projection in x, which is always always the same, Vx V naught cosine theta, and a Vy that keeps changing all the time. So Vx at the highest point is also equal to this velocity here, right? So we have it that. So this is equal to my V at the maximum point. V at the maximum point right here. So it's the same. Well, now it's simple. V max, which we calculated in the first part, is equal to V naught cosine theta, or 15, because that's the value of V naught cosine theta. So our cosine theta is equal to V max, which we calculated, divided by 15. And then you can find your angle. Okay? The last problem, you have a block of mass 2 kilograms that moves with a speed of 4.5 meters per second. The surface is frictionless, right? There is no friction, and so the block is here, it's moving to the right, and right there is a nice spring. So of course it's gonna excuse me, it's gonna hit this spring and compress it. Oh Jesus! Right? Which means this distance here is how much of the spring was compressed. And we want to find what is the maximum compression of the spring. The spring constant is given, 450. So this is also my simple problem that it just implies directly application of your expression. I have converted kinetic energy exactly at the point the block is about to compress the spring. The block has a kinetic energy which is equal to half mass of the block, velocity square, and that is going to be equal to how much of the block was entirely compressed. So the only thing I do is to replace mass by 2, the velocity goes in here, the spring constant is placed in there, and then we can have our dx. This is a square root of m divided by k times m divided by k times v square, so 4.5 square, and then we have that much in meters. Okay, so that was our exam, and let me know what you think. Okay, bye.